resorcinity actually sense anions or replace aromatic?
It will behave the same way. It will behave the same way as that of the resorcinary. They are similar in character, but the main difference between these two are is that it is chiral. It can be chiral because their nature as such, they are existing as R and S enantiomers. So if you separate them, right, it can selectively recognize one another chiral molecule. So R could sense probably S alone, then you can make a chiral recognition basically. So that is the advantage of that skeleton, whereas this cannot do that. Okay, so there is no matching of R and S.
It's fine, I'll speak loudly. Sir, so we've been like in school, we've been told about these confirmatory tests for different anions.
Yeah.
Why do we need like these complex things when we can just test like fluorides and stuff with those confirmatory tests?
That will tell you whether they are present or not.
That's what testing, like we're just trying to find out if it's there.
No. You're just capturing, removing it. Yeah, that's only checking. You may check whether the water is contaminated with fluoride. You decide now. Okay, now this water is contaminated with fluoride or more amount of nickel 2+ ions or Hg 2+ ions which are toxic. These tests you could do with those qualitative tests that you are doing, right? But you want to recover them. That's where these microcycles come into picture. You can capture all the fluorides that are present there. You can capture mercury ions that is present there, right? You can filter them basically, filtration basically, right? So just collect all of them, complex them, and then reuse it or recover it for some other purpose.
Also, we can use simpler substances to like separate fluoride ions. Why do we need complex substances like heterocalyx arenes?
Here you are not having a covalent bond between the fluoride and the macrocycle. There is no covalent bond. You understand? What it is doing is to it just interacts weakly with these macrocycles, so that you are able to dissociate it at a later stage and collect it. So binding and dissociation, both are possible. But if it covalently binds in other systems like what you are saying, like precipitation, you can get rid of the fluoride. Then it binds, you cannot collect it and reuse. Right? So that's the problem. Yeah.
Sir, after fluoride is captured in the molecule, how would you separate it from, say, water to actually make the water usable?
You can dissociate it by various means. Like I said, pH is one of the ways. You can modify the pH, you can collect the fluoride. You can also supply thermal energy, reflux the solution, dissociate them, and then recover it. So various means by which you can dissociate, because these are generally weak interactions. There is no covalent bonds established between the incoming guest and the host, so it could be dissociated.
Sir, so the interaction between the host and the guest is purely ionic and dipole interaction.
Not necessarily. The various other interactions, such as hydrogen bonding, can come into picture. Pi-pi interactions can come into picture. Donor-acceptor interactions can come into picture.
So any bond, any interaction that is not a covalent bond, we are okay with this.
That is where it is called a chemistry beyond the molecule. Within the molecule, we always talk about, inductive effect, mesomeric effect, right? Bonding, sigma, pi, and all that. But it is interaction between one molecule and another molecule. So it is basically intermolecular interaction or molecule-ion interaction is what you are talking about. So it is an interaction basically. So it's weak. Okay. Yeah. Any other questions? Okay. So we'll move on. In continuation to what we have been discussing. Okay. Look at this particular skeleton. What it misses is the hydroxy groups. Correct? If you look at resorcinarenes, you had hydroxy group here. 1, 3, 1, 3, 1, 3, 1, 3. If it is methoxy tetramethoxy resorcinarene, then you had methoxy on this side, this side, this side, that side. hydroxy is at the third position from the methoxy. If it is calixarin, you had hydroxy groups pointing inwards, right, with the tertiary butyl groups on the para. That was the arrangement. Now here there is no hydrogen bonding units present in this skeleton. Okay. So it is called metacyclophane because you connected these benzene rings at the meta position, 1 and 3 positions, they are interconnected. Given this scenario, how do you think this molecule will behave? When you put them in solution, because there is nothing to hold. There was hydrogen bonding, so it could, all these arms could be tied through hydrogen bonds. Now in this case, there is no hydrogen bonding interaction. How do you think these arms would be? The, it would? It is already joined now through this methylene. Now there is no way that it can, these hydrogen bonding could hold themselves together. It should be very flexible, correct? So it can shuffle back and forth and keep moving, right? But tying these arms, 4 of you stand together, right, and then dance around. So that's how this molecule is going to behave. So you can go back, friend, do all this dance, but there's no way that they can stay rigid, right? Because the hydrogen bonding keeps it quite tied and there's no flexibility. But here there can be a lot of flexibility. So you can see a lot of conformations that it can undergo. If it isn't this conformation, which we call it as boat, because 2 arms are pointing at the top and 2 arms are flat, looking somewhat similar to that of boat, right? But it can, if it has to go from boat to the boat, another form of boat, it has to pass through crown. You understand? So these 2 arms, 1 and 3 benzene rings, right, it has to come to the crown. Then you can see these 2 arms going up and these 2 arms would become flat. Okay. So this is kind of a transition state for these 2. Can we say that? So just to start from here, if it has to achieve this conformation, it has to go through that state and then come to the another boat. Okay. So this is the conformational freedom these molecules have, right? Now we have taken up the same example here, what we discussed earlier. This is the hydroxy containing arenes. Now these hydroxy containing arenes are establishing hydrogen bonds. This molecule will have no conformational mobility or freedom, right? Because these arms are tied by hydrogen bond. You tie them up, right? So is another structure. People have also developed covalently tethered macrocycles, where these 2 hydrogen bonds are connected covalently and they have tied them up through a linker. Some substitution is there and you just, build this, and that is also quite rigid because it never allows this arene to flip-flop. There is no way that it can flip-flop. So they are now looking perfectly like a crown. This is looking a crown because of the intramolecular hydrogen bonding, right? This is behaving crown because of the covalent tether, right? Now, these, yeah, please.
Sir, the clavicle, the tethered one.
Yeah, post macrocycles. Yes.
There do the R primes need to be the same? Because symmetry.
Usually it is same because you start with the R prime containing unit for doing this reaction. Rarely you would end up in partially connected ones. It is very complex if you get a partially connected one. So the tendency is to push it so that you complete the reaction to get this, rigidified macrocycle, right? So R prime, if it is uniform, it's easy, your life is simple. Otherwise, it's going to be troublesome. Yeah.
There's a bell curve over this. There's a bell
Yeah.
What is that energy answer?
It just represents the energy profile because this is the low energy conformation, right? from this low energy state to this low energy conformation, if it has to go through the high energy conformation and then release this. Like what we saw from a staggered form to an eclipsed form, it has to have this CH eclipsing interactions. It has to overcome this. At this point, you have the maximum energy and then it decreases, right? So here also, from one conformation to another conformation, it has to pass through this barrier to go to the other conformation, which is again a low energy conformation.
Yes, thank you, sir.
Okay. So generally these macro cycles, if you look at, they are not very luminescent. They are not light emissive. Okay, because the conjugation is only simple benzene. That is the only unit that is conjugated there. Whatever you do, you change the benzene to heteroarene. Again, it is confined within that small ring. There is no extension of conjugation possible. So most of these molecules are ultraviolet emissive. They emit in the ultraviolet region, which you cannot see. Okay, so that is the drawback of it. But people wanted this to be fluorescent, right? So that you can detect through our naked eyes. So what happens was they just incorporated various fluorophores on the periphery. Anthracene is fluorescent, it's a conjugated molecule, and you can excite this and then achieve luminescence from this. Instead, this acts as just a scaffold, right? It helps these anthracene molecules to come close by. If a guest comes in to the cavity, then these anthracenes would sense, hey, some guy is coming in, right? It modulates, it tries to modulate my emission, right? So it would just sense it. It would send a signal out, right? The guest comes in. So these fluorophores can do this job of monitoring the guest coming in. If it is in, it can convey the information. If the guest is released, it can give the information as well. So you know the guest is in or out. Okay? Yeah.
So the way it conveys information is by changes in luminescence.
Correct. Intensity wise or the position wise, you will see the modulations.
What's the position of?
Position of the emission. Okay. So let's say if it emits in the blue region, it can shift a little bit to the green or blue green. So it will give you an indication. Or sometimes if the guest is absorbing that light energy, right, then you will see the emission intensity coming down. You say, hey, something has absorbed my energy, right, for its survival. So you will see the changes, which is very helpful for you to identify if indeed there is a host guest complexation occurring.
So can we see this reaction sometimes?
Yes, you can. Why not?
I want to see the light.
Okay, so this is yeah, please.
So sir, is this also used for the drugs applications?
Yes, drug application. These are mainly sensing applications.
So because anthracene is carcinogenic.
Pyrene is more carcinogenic than anthracene.
Is it?
Yeah, 4 rings.
NCERT, no, sir, like in that pyridine is not listed under the carcinogenic at all. Like anthracene and like other big chains are. So that's why I asked.
It can be, but pyrene is yeah, serious. 4 ring fused systems. You don't have pyrene in your DNA, no? Yeah, purine, pyrimidine are the bases that you have, but pyrene no, right? So these fluorophores are anchored for that purpose. But please remember, synthesizing macrocycle itself is challenging. Attaching these fluorophores after the synthesis is going to be even more challenging. Yes, it's an extra step involved in the synthesis. Okay? So that's tedious process. Okay? So you have to ensure that if you are attaching it to 4, you have to ensure that all 4 are reacted to form this. No? 4 of such units are incorporated. So that's very, very crucial, and it needs basically extra synthetic efforts. Okay? So what we thought was, it's our laboratory results, just few results here and there. So what we have done was we made this heteroaromatic unit that you saw previously. If this itself could be fluorescent, right, then when we are making the macrocycle, we would embed the fluorescent aspect into it. So we don't need to add any extra steps to it. Okay? That was the idea. So one of the fluorophores of heteroaromatic nature came to our mind was simple coumarin. Okay? So it is the pyranone annulated benzene. Have you seen this molecule anywhere? Coumarin alone. Don't worry about the four. Just look at this only one structure here. One ring. The bicyclic compound that you are seeing. You have not seen this?
Where do you think you would have seen?
At home.
Sir, cow we have seen, sir.
Okay. Okay, you must have eaten this already. Coumarin, yeah.
No, you're asking which from cumin.
Cumin seeds or cumin.
Not in cumin seeds. Cinnamon. 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 Cinnamon has this particular molecule.
I don't like it.
Oh, cinnamon you don't like?
I don't like that one.
That's a flavoring agent they use in masalas, right? So the cinnamon has this coumarin unit, and it is very bio-friendly, right? And one of the derivatives of coumarin people use is warfarin. Warfarin is a drug, okay? It's used popularly as an anticoagulant, right? In a case of thinning agent and stuff, right? So people may be injecting. So that is one of the drugs. Warfarin is a drug which is composed of coumarin. Okay, so in many cases you would have come across, but anyway, just that you don't know that coumarin is present in cinnamon. Okay, so this is very bio-friendly, and it has a fluorescence nature also. It emits blue light. When you shine it with a particular wavelength, it gives out blue light. Okay, so we thought we can easily make this unit, the macrocycle composed of coumarin as such, so that further functionalization to anchor these fluorophores is not necessary. Okay, but how do you make it? You can make this from simple phenols. You can take the phenol, this or this. You can easily convert that to coumarins by doing a simple Pechmann condensation reaction. Right? Pechmann condensation reaction. Go back and read about it. Okay. Pechmann condensation reaction, right? Yeah.
Can you please repeat the covalent, non-covalent methods?
Non-covalent method is through hydrogen bonding. Covalent method is through real covalent bonds. Okay, so hydrogen bonding makes this crown. Their covalent tethering makes this as a crown. Right?
So that one is the most flexible. First one is the most flexible.
This is the most flexible one because it doesn't have any covalent tethering or hydrogen bonding.
Yes, sir.
Through hydrogen bonding, you have made a crown. They made it less flexible.
Yes, sir.
Okay, this can be broken because it's weak interaction. It's a hydrogen bond. It could be broken. So whenever it is broken, it could behave like this.
Yes, sir.
Okay, but here when you tie it with a covalent linkage, there is no way you can break it. They are always rigid.
Yes, sir.
Okay, so till now in the literature there is only one method available by covalent tethering. You can rigidify this macrocycle. You can arrest the flip-flop motions of these arenes.
Yes, sir.
Okay, so this is the only method known. So what we thought was we want to functionalize the core to make the macrocycle luminescent. So the macrocycle will be ultimately emissive in nature. Okay, they can give out blue light. So we did that, and how we did it, I don't know whether, yeah, we have the steps here, right? So we started off with this methoxyphenol, do a simple condensation reaction. you form the tetramethoxy macrocycle, right? Afterwards, you cyclize this part, introduce this part into the ring, and you can make the coumarin. Which part? Yeah, this coumarin, you have this reagent which is Meldrum's acid and Yetton's reagent. Yetton's reagent is a condensation reagent, and this Meldrum's acid liberates this particular unit upon heating, and then it is cyclizing. Okay, so you ultimately get this tetrameric compound. Once you have, yeah.
What was the yield percent for that finally?
Percentage yields are denoted here.
Oh, okay, yeah.
Okay, because we also wanted to vary the alkyl group that are present there by R. Okay, we varied the R groups, aldehydes basically. So in one case aldehyde was acetaldehyde and then propanaldehyde and so on and so forth. We varied the alkyls, correct? And we also had branched aldehydes, branched alkyl chains, aldehydes with branched alkyl chains. We also had cyclohexyl carboxaldehyde, so on. We varied these aldehydes. You get varying yields, of course. Okay, starting from 37% for 2 steps, for both the steps, and then you see for there is an increase and then there is decrease further. Okay, so this work was particularly highlighted in this journal. Okay, they wrote a comment saying that this is a very promising macrocycle which was not reported before, and this has inbuilt this luminescent properties inherent. So this is one of it. Thank you. This is simple information. You don't need to. Okay. So here, this is where your attention have to go. Okay, this is where your attention has to go. Where when you change the alkyl functionality from methyl to ethyl to isobutyl to propyl. Okay. When you vary the branching chain, right? So which means from methyl to ethyl, CH2, CH3, and then isopropyl, right? And then tertiary butyl. When you have tertiary butyl groups, I didn't get any of these macrocyclic products. This is R is equal to tertiary butyl. We didn't get any macrocycle. When you have to explain me now. So this is isopropyl, right? In isopropyl, I am able to get 48% of the yield macrocycle. And if I come to ethyl and methyl, methyl again decreases. That's because of the solubility reasons. Ethyl you can get up to 62% of the product formation. Where is the steric hindrance? It's a bulky group, so what does it do?
At the bottom, when you have that funnel shape, then they have to find the space.
Yeah, so the R groups are hanging, right? So so they would repel each other. There is no space, right? So these R groups are located at the bottom. So if there is a big tertiary butyl group, there is no sufficient space for it, and hence it doesn't ring close. So if it has to forcibly close, it becomes severely strained. Okay. Instead, it would avoid forming a ring and they being linear actually. So in that case, we are not able to isolate the macrocyclic product. This gave us a clue. What was the clue we learned from this was, okay, you can also use the alkyl groups and their bulkiness to arrest this conformational flexibility. Okay, so that was the development, that was the message that these reactions could give, but we have to confirm it, what we understood was correct or not, right? So what we did a set of NMR spectroscopic measurements. You may not get any of it from here, because without understanding the NMR spectroscopy, it is difficult for you to explain. But what I can tell you is, just look at this structure. When it is isobutyl, branching is away from the alpha carbon, you find that there is a fast equilibrium between this form and its other conformational isomeric form, wherein this arm would come up and these two arms would open up. Okay? This is the case of isobutyl. In the case of isopropyl, right? When you look at this, I don't have any hydrogen bonding interactions there in the molecule as such, right? But what it has done is, it has already given me a crown conformation. How? Because if you have the tertibutyl here, keep in mind there are 3 methyls attached to every carbon there, and each of the carbons would force one methyl to be inside this space, right? Since I have removed that methyl for isopropyl group, it keeps one hydrogen inside, leaving the 2 methyls away. So the void space inside is sufficient enough to keep only 1 hydrogen per carbon. It can allow only 1 hydrogen per carbon. That's like a cap sitting on the top of the funnel and blocking this entry. If you just imagine that you keep 1 more methyl inside, obviously that's going to not let the other part of the ring to come close by, right? So because that's going to push this away. So it doesn't have a sufficient space to keep a methyl inside. And that's why we learned that there is no product formation of the macrocell. So for the conformational rigidity to implement into the skeleton, what you need is to be implemented into the skeleton. What you need is isopropyl is good enough for you to do the job. This is the message, okay? The NMR spectroscopy, you can just forget about it, but what it tells you is it's a symmetrical compound. Whatever temperature you vary, it is quite rigid, right? But in the case of this isobutyl one or ethyl also does the same. If you vary the temperature, they become quite flexible, as you can see here. 2 signals become 1 signal. Again, you do the reversible process from 1 signal to 2 signals. Yeah.
So, as a scientist, how would you know what to mix to make such a complicated structure? How would you know what this structure would be used for?
Yeah, what this structure would be useful for?
Yes, so like all of these structures, to be honest.
Yeah, so you need all this data to, initially you have some hypothesis in mind, okay? So this is how I need to make a design and then verify if it is going to be happening or not. So you test out all your hypotheses, check with all these results and data, see if it is falling in alignment. If it is following the assumption that you made, then there is a drive to it. Okay, we are going the right direction, it's going to happen. So push it as much as possible. Okay, so that is so you need all these data and then systematically analyze them, which will, whether we are going in the right direction, we will come to know. So these experiments gave us a clue basically. Because when we vary the temperature, it doesn't undergo any conformational changes. Whereas this one, when you vary the temperature in the same solvent, it could undergo flexible motions. And solid state X-ray structures have also revealed that one is having a boat conformation, which means once you formed a boat, it should go to another boat. So there is a possibility for conformational mobility. Whereas here, once it is locked in crown, it's ever going to be in crown.
But how do you know that these structures are possible in the first place, sir?
By modeling, you can confirm. Modeling, yeah. You can do an energy optimization structure separately. You can calculate the structures. You can compute them and then see if at all it is giving you a crown beforehand. But we didn't do that way.
Sir, have you built like proprietary software for it?
Proprietary software for
the modeling?
Oh, no, we don't have anything.
Software.
I take the help from Professor Mangaleshwar. Okay, he has a very sophisticated computational facility, right? So they could just process all this data and then see if they can come up with a structure is feasible or not. And they can even compute how much is the difference between these conformational isomers. Okay, so you can compute them, but we did the reverse. We did the experiments first, and then we took the help of the theory to see if our understanding is correct or not.
So when you said we use these to test for ions and like remove them from when we pass liquids over them, you said that we have to attach them to a substrate.
Right.
So how do you attach it to the substrate?
One of these functionalities could be used either through the alkyl. You can modify the alkyls through, you can attach alkyl substituents which has a carboxylic functionality or something. The surface is polar, you can just anchor them to it. It could be an inorganic substrate as well. These carboxylic groups are good at it, they would go and bind. So you can modify the substrate using this R linker or from the hydroxyl linker, you can modify them.
I have a question about the interpretation of the MR graph. So what is a star at the very bottom at 25 degrees Celsius?
This is a small star that you're talking about.
Yes.
That is the solvent. That is the solvent that we use for this characterization. Okay. So
specifically, there's a solvent using that 25 degrees Celsius.
Yeah.
And you said something about the two different.
No, that's not only at 25 degrees. It's the sample having this, which is seen in every temperature. So it's a machine which has a capability to vary the temperature. But you place the sample has this star, right? So you vary the temperature, and at every temperature you record what changes that you see. And the spectrum can be stacked one on top of each other.
So you also said something along the lines of the two peaks joining together to make one peak, right?
Yeah.
What does that represent?
Okay, I tell you qualitatively, right? This single peak, meaning that there is a very rapid conformation, the shuttle between the boat and boat. Okay, so the time scale is so fast. Like we saw for ethane, it is 10 to the power 11 per second. Here it could be much more faster, or not much more, sorry. It is also faster that the machine is not able to distinguish these two states. So it is an averaged state. Average state is what? It is ultimately the crown, right? Two arms going up and two arms down very rapidly. Let's say on an average you would see in a given time frame, you would see this behaving like a crown, right? So the machine is not able to distinguish at room temperature. So that means the barrier from boat to boat is not so much, it's not that much, right? So machine sees it as one. But if you lower the temperature, you can make this conformational equilibrium, little slow, right? And then the machine is able to detect, and it can say, hey, now you have two conformers. Look, there is one signal for that and another signal for that. Okay, so the machine is able to distinguish. NMR spectroscopy can distinguish up to few milliseconds, not more than that. If it's very fast, right, more than that, say microseconds or nanoseconds, certainly NMR is not going to differentiate between the states. So it appears at room temperature they are very fast, right, much faster than the millisecond time scale, and the machine could not distinguish. So at room temperature you will see only the averaged conformation. At a lower temperature, yes, you can distinguish. But that's not the case when you have isopropyl substituted groups. Okay, so you have only one form irrespective of the temperature. There only one form, that means it's quite rigid. Okay. Yeah.
At those smaller time scales, NMR doesn't work. So, what other technology do we employ?
For distinguishing such fast ones?
Yeah, at faster and smaller time scales.
But conformational mobilities you want to check with respect to the time scales, usually NMR should work, but NMR can indirectly give you the information. Like we can predict that, okay, time scales are faster than millisecond time scale. You can also say the barrier could be typically around this region, say 10 kilocal per mole or something. Okay, this you could gauge based on the NMR studies. But if you really want to observe these two, then you have to use that particular time scale studies. For example, lifetimes you can use fluorescence spectrophotometer. You have to use that particular time scale spectroscopy to identify if these two conformations could be distinguished. Okay.
Sir, if you notice in this graph, at between 5 and 6,
yeah,
at all temperatures, the black line is converging at the top. So that does mean at that point, it's always it's shifting rapidly at all temperatures.
which one? The black line, this one?
Yes.
This black line. This black line is again a solvent that is used for the spectroscopy. Okay. It is 5.2. So it is a dichloromethane as a solvent. Deuterated form of dichloromethane is what is used as a solvent. Okay. And these are the signals that are for the compound, which you find that they are resolving into 2. Okay. So it's confirming that there are 2. Yeah, please.
Right below the line right below -70, when it goes to the black section, the purple section doesn't connect to it. It just dips.
Here. Yeah.
-70.
-70. This line.
No, goes to the right. Yeah, both there.
Here.
Yeah, that goes down, but it doesn't connect. Why is that?
Yeah, it must have connected at some point. It would have gone down and it must have connected to the middle, the black line that you're seeing there. So it is kind of a derivative curve that you have it there. Okay, it's not a signal like this, but it's a derivative curve, right? So when you plot it, probably it is below that axis, so you are not able to see, right? So there is a small disconnection, but otherwise all of them would connect at that particular curve. Okay, so it's kind of a differential curve is what you are seeing. Yeah, okay, fine. So this is the solid state structures. Whatever you are seeing here are crystal structures, right? The student was very good in crystallizing these compounds, and these are all in solid state. So you actually know what is the thermodynamically stable form it is in, right? And this particular macrocycle that you have, the substituents are shown there, ethyl, okay? The big ones that are shown there are the alkyl groups, and this is the skeletal information of that arene, right? And what you are seeing basically is you can see the arenes going up and coming down. You can see this is slightly pushed by these alkyl groups that are there. Initially it was like a butterfly raising the wings, and you see that it's slowly becoming flattened, and if you increase the alkyl substituent to isobutyl to cyclohexyl, pushed down, right? And then isopropyl, it's further more down. So if you image this one over the other and do a quick animation, they would see that, you would see, right? They would be flipping their arms. So this is a top view of this molecule. As you can see, when you go from ethyl to isobutyl to cyclohexyl to isopropyl, you can see the crowding is significantly increased, right? The crowding at this part is little more. Just imagine this is the hydrogen pointing inwards, and these two are the methyls. Just replace this hydrogen by a methyl, it's going to be overcrowded, right? We could also luckily crystallize this macrocycle, which we made, right? And here again, if you compare isobutyl versus cyclohexyl versus isopropyl, you are seeing these arene part folding in, and now you have ultimately achieved a crown. Top view, if you look at from isobutyl to cyclohexyl, it has become a little crowded. If you add one more methyl and then keep the hydrogens pointing inwards, that is the space that you have. By putting one more methyl here, you can imagine it's going to be very crowded, because in the hydrogens place you are going to keep a carbon, and then you attach 3 hydrogens to it, and that's the space it has actually. It cannot accommodate 3 methyls within the cavity. Okay. So this is what is understood by single crystal X-ray structures, and you can, if you are able to crystallize the compound, you can get the solid state structures of them. You can see how the molecules are arranged in the solid state, how they can pack, right. So all that information you can know. You can also calculate the pi-pi interactions between them, hydrogen bonding interactions between them, weak interactions between them. All of that you will be able to look at by using the by getting the solid state X-ray structures. Okay. Now again, coming to the discussion that we made that day, analyzing from methyl to isopropyl, right? What do you actually see? Initially you started off with the torsional interaction, CH, right? This CH would eclipse with this CH, right? And it wouldn't like, so that's a high energy conformation, it would tilt, forming a staggered, and you can have 4 of such staggered conformations because each of the carbons are holding a methyl, right? They are all 4 rotors sitting on each of the carbons, and that is a structure that you call it as boat. Ethyl also has that boat to boat conformation interconversion, right? And when you have one methyl here, let us say ethyl, methyl to ethyl, you are bringing in the Gaussian interaction, methyl and phenyl ring having a Gaussian interaction. How many of these Gaussian interactions are there? 1, 2, 3, 4, and this methyl could be here, you can generate this one. So you can also have Gaussian interactions. You can have Gaussian interactions which is when the methyls are inside. When methyls are inside, you have 2 Gaussian interactions per methyl, right? So that will lead to 4. So 8 versus 4. So that is a low energy conformation and this is a high energy conformation, and most likely molecule doesn't stay here, it stays in this form, and this is the form we saw in the solid state structure also, right. So the observation is nicely correlating, and if you go to the next one where R is equal to isopropyl, you have 2 methyls instead of 1 methyl in the case of ethyl. So now you have 2 methyls you have incorporated, so each carbon will have 2 Gaussian interactions, right, this side and this side. Similarly here and here, how many of that totally? 8 of the Gaussian interactions. So what you are basically doing is by adding extra methyls, you are increasing the energy of the system, okay. And if you are having tertiary butyl, how many Gaussian interactions you can encounter per carbon? 1, 2, 3, 4. So for 4 carbons, it's going to be 16 Gaussian interactions, which is going to be leading to a very high energy conformer, right? And sterics at the central part, okay? And that's going, these methyls are going to push against each other. So they would not permit the ring to close, and that's what we saw during the reaction. We didn't get the cyclic product, okay? So the conformational analysis, you can use it to design macrocycles. You can arrest their conformational motions and make it more specific. You can make the crown with a specified void size very beautifully, okay? So that was one thing. And we also calculated the ring strain, right? Because you keep adding the methyls, what you did was you are increasing the strain energy at every carbon centers. Yeah.
Sir, I thought tertiary butyl didn't provide the curve, right?
If it did, it would look like that.
Okay. So, sir, just to confirm, tertiary butyl, when you tried it in the laboratory, we couldn't get a crown structure.
Yeah, you couldn't get the crown.
So this would be hypothetical if we did get a crown.
Correct. These are calculations.
Okay.
These are calculations, and calculations indeed did not give you a crown, but it gave a pinched crown. It's not perfect like this, because if you are forcibly putting these additional methyls in, and they are asking the software to do the calculations. It tries to do, but it doesn't achieve the perfect count, but instead it is, the sphenyl rings are not exactly aligned one over the other. But when you have a side view, they would see that they are pinched, right? So you don't have a perfect crown as a result of this, and it has to do that way because it has to accommodate these methods. But in reality, it is not happening when it forms the macrocycle because it cannot withstand that strain energy, so it just opens.
Is a pinch crown being formed because it's more stable than actual crown?
Now, pinch crown is not formed at all. This is a calculated structure. It's the software gives you. Okay? In reality, you cannot make it in the laboratory. So we are trying to know the reason why it is not formed. Yeah, it's very high energy and it is quite unstable. If at all it is formed, it should be a pinched crown. Right? And anyway, we are not getting it in the reaction. So that's the connection. Whatever.
So what is the furthest you have made the ring to come closest to, sir?
Yeah.
So what is the furthest, like you said pinch crown is not possible. What is the furthest you have brought the structure to, sir?
We could get up to crown. We could get up to crown. Up to crown. So you cannot put a tertiary to make it pinched crown.
Pinch crown is where it's closer.
No, pinched crown is, perfect crown would look both the side, the opposite phenyls or the arenes would exactly, would be like a mirror image. Okay. But now in a pinched crown scenario, you would see this twisted. Okay. So they don't align exactly one on top, but they would have some twist. Because like we said in the cyclopropane, these eclipsing interactions are seen, 6 of them, right? But if you go to cyclobutane or cyclopentane, the molecule will not remain in planar form, right? Because more the eclipsing interactions, they would try to avoid these eclipsing interactions, so they would just pucker. So the rings wouldn't be planar. That is one of the reasons why the cyclohexane is existing in chair and boat forms. Okay? Let's say you take the chair form of cyclohexane, press it, make sure you are forcibly making it planar, putting all the carbons on the plane. Right? Then these hydrogens you would have, how many of the eclipsing hydrogens you would have? 6 on top, 6 at the bottom. There will be 12 eclipsing interactions the molecule wouldn't want to face. So what it would do instead is this, to try to avoid these eclipsing interactions by twisting. Right? So that happens on every carbon, you would end up in a more stable structure which is boat, chair. Right? And the chair, again it moves to boat. In boat again you will have eclipsing interactions, but the number of eclipsing interactions is not, they are not as high as that of the planar cyclohexane. Okay? So molecule would try to minimize this, right? The interactions that are imposed on. So try to keep it very minimal so that they can be stable in the form. So similarly here, that's what you would see, right? When you put more methyls on the bottom part of it, they would try to avoid from each other, and hence these rings are not exactly overlaying one on top, but it would just twist, resulting in a pinched crown conformation. Okay. What happened? Hey, you have not taken a break. I thought you would need a break between the two. No? We must have had a break.
We'll finish it after 4 o'clock.
After 4 o'clock. Okay. I will try to be fast. So strain energy is also increasing. Ring strain energy, you see that it is increasing upon increasing the number of methyl substituents. Okay. So yeah, once we know this, what we thought, we measured the diameter of this crown that we had with isopropyl. The diameter was around 13.5 angstrom. from this aromatic ring to the other aromatic ring. If you measure from this tip to that tip, it was about 13.5. So it's quite wide enough. And this is one of the largest macrocycles known at that point of time. Okay, and it is luminescent. And it was also luminescent. So what we thought was
More development has happened.
yeah,
2 years.
around 2 years. Publication took another 2 years. Okay, so a lot of fine tuning has to be done, and still there are modifications going on in the laboratory. So see, what you have to take into account is, since the void is about 13.5, an equivalently bigger size molecule is fullerene, C60, right? If you measure the diameter of fullerene, including the van der Waals radii, it reaches close to 10 angstrom. So if you put into this, then it would be very appropriate, we thought, to fit in the void, right? So we initially tried to titrate this. Titrations you all must have done, right? So similarly, we took a solution of fullerene, kept adding the solution of fullerene into the macrocycle, hoping that since it is rigid, so it is always open, so it would incorporate the fullerene. If at all, it can establish an attractive interaction, very strong attractive interaction. But it did not happen. We went up to 300 equivalents. There is no binding seen. In principle, what you need is, for one macrocycle, you would expect one molecule of fullerene. So 1:1 stoichiometry should be good enough. So we pushed it up to 300 equivalents. Can you see? So even after that, there was no incorporation of fullerene seen, right? So we could plot that, and every nanometers we plotted, there is no saturation seen, meaning that there is no complexation observed. Okay, but interestingly, while you are titrating, not only the absorption spectrum, you could also monitor it through fluorescence, because the macrocycle as such is fluorescent. So you would come to know if at all there is an interaction or not. Okay, so we monitored the fluorescence spectrum, and initially, to begin with, it was this at 0 equivalence. Upon titrating, going up to 20 equivalents itself, you could see the luminescence coming close to 0. Molecule was not emitting at all in 20 equivalents. It is absorbed by the fullerene, but the process looks to be very dynamic, right? Let's say there is a macrocycle, it gives out the blue light, and you have good number of fullerenes. They come collide. At that moment, there is a loss of emission. It goes away. Another molecule of fullerene comes, collides, goes away. So this interaction seems to be very dynamic. It is not favorably forming a complexation between the macrocycle and the fullerene, which means one molecule approaches the other molecule, collides, and if the collision is fruitful, it should bind and then stick together, right? But that is not happening. Looks to be very weak. So they come, hit each other, depart, right? So that's a dynamic interactions, and the dynamic interactions machines could sense. With more number of fullerene molecules around, you are able to quench the luminescence to completely 0. So the solution was not at all emissive moment you add 20 equivalents of fullerene. Okay, so we realized that there is some dynamic interactions. NMR spectroscopy we could also do, and there is no signal shift. If there is a binding, it must have shown in a different way, which we don't see, and the signal exactly matching upon titration, and dynamism is again fast, that the NMR spectroscopy could not detect. The time scales, right? The collision time scales are quite faster, and the NMR could not differentiate. But we know that, we understand that it is dynamic through NMR spectroscopy. So no complexation in solution at room temperature. So it is not giving fruitful result, right? So we were a little upset, but then we thought, okay, we will increase the number of collisions. So that, yeah, please.
So what would the graph of a saturation look like?
It is increasing now, and at some point when the complexation is over, you would see flat. Okay, so it should reach this flattening. That's when you see it as complexation is achieved. But right now what we are seeing is keep on increasing. That means every time there is collision and it doesn't result in a productive complexation, right? So that is the graph indication. Yeah.
What is rigidification?
You have to go back. That isopropyl group when we introduce, we said that the conformational mobility is arrested, right? And that's what we call it as conformational rigidification. Okay. So that is played by the alkyl substituent that is on the lower part of these macrocycles. Okay. So this is the isopropyl group. This isopropyl group brings in the rigidity to the macrocycle. It always keeps it in crown. Okay, that's the rigidification. So then we thought we increase the temperature. In room temperature, the phenomenon does not happen. So we improve the number of collisions. So what we did was we increased the temperature to toluene reflux. Toluene is a solvent basically. Why we use toluene is because fluorines are hydrocarbons and hence they are soluble in hydrocarbon solvents, right? So toluene is one of the hydrocarbon solvents where fluorine is found to have a very good solubility. If you choose the dichloromethane or chloroform and all, fluorine has a very poor solubility. You cannot dissolve them. So you need a aromatic hydrocarbon solvent such as toluene to dissolve them. To begin with, the solution is like this because fluorine's color is this. If you dissolve it in toluene, fluorine gives this purple color, right? And you add this macrocycle to it, you reflux it for 24 hours and the color of the solution changes to orange, brown color or whatever, right? So immediately student ran to my office and said, "Sir, color changed. Color changed." Then I said, "What happened? Color change means what?" "No sir, we also see, so there's something precipitated. You can see at the bottom some brown stuff, right? Did it happen before?" "No, I'm seeing it." "Okay, then we'll characterize it." So this formed a very nice precipitate at the end of it, gave us a clue that probably it could be a complexation. So the first thing that we did was to try the solubility in different solvents. One of the graph is shown here. We took simple dichloromethane where macrocycle is soluble but fluorine is not soluble, okay? And if you take simple macrocycle, it is soluble, as you can see, clear solution. If you dissolve fluorine, it has a very limited solubility up to this much concentration, which is also shown in dichloromethane as a solvent. But this precipitated solid, after drying it, you dissolve it in dichloromethane, you find a nice dispersion of this complex into the solution, into the solvent. The concentration is much more higher than a simple fluorine could dissolve in a dichloromethane solvent. So that gave us even more hope, saying that okay, probably we formed a complex and the complex is soluble, right? And if you just take the toluene reflux solid, and that also can improve the solubility up to 2.15 molar, which is roughly 4 times, close to 4 times of this concentration by just grinding. So we realize that solubility has improved, that means complexation is formed. Okay, but we also, that is alone is not enough. Solubility test is a very preliminary test which cannot confirm that actually there is a complexation formed. Okay, so yeah, 5 is the compound's name. It's a code for the compound 5E, right? So 5E here denotes this compound. So again, yeah.
At the end, did you get the results that it actually did form a complex?
Yes.
So that even after all those tests, it's still a complex.
Yeah, it is complex. So these tests are all step by step proving that you have a complex, you have a complex. So again, we can also monitor it by emission, right? So you see how luminescent this macrocycle is. Okay. Previously, I didn't show you the photograph of this emissive macrocycle. Now this 5E denotes this compound alone. Alone it is blue fluorescent. Not only in solution, in solid they are luminescent. Okay, it gives out the light. And when you mix it with C60, there is a significant amount of quenching. And you can also see the emission shifting, emission wavelength, right? So which is corresponding to 450 nanometers or so, is now shifted to 500 and above. Okay. So this indicated that there is certainly a complexation between the two, but we were not sure about what is the stoichiometry of them. We thought at that point of time 1:1 only, but we have to verify, right? There are other experiments that have to come into picture. And this is a simple thing that we did also, right? We took the solids because the void is pre-organized, so always open in solid state. So we took the C60 powder, we ground them using a mortar and pestle. You can grind them together, and after grinding for about 45 minutes, adding few drops of dichloromethane, the solid turned this color. And you can also now check if at all you have formed a complex just by grinding. Initially it is black color. C60 is solid is that color, right? And your compound is colorless. Under ultraviolet light, the same solid gives you the blue light. When you shine ultraviolet light, this is the emission you get from the solid, right? You mix it with C60 and grind, the solid color becomes like this, right? So then we started characterizing this ground sample. You will see that various studies were done. So proton NMR spectroscopy, diffusion rate constant, because the size of the complex is now grown up, right? It should diffuse slowly than that of the individual counterparts, right? So we measured the diffusion constant, proving again the rate of the diffusion is slower than that of the individual ones, and we also checked the composition of them using mass spectrometry, which gave us a confirmation that is again 1:1 complexation surrounded by some 1 or 2 solvent molecules supporting this association of them. So all of that is confirmed, and we then concluded that okay, we have a 1:1 complexation of the fullerene and this one. Similar experiments were carried out for the flexible system also. Flexible system in a sense, the isobutyl one. None of the cases you had the complexation. You reflex, it doesn't complex. Room temperature 300 equivalents, it refused to complex, right? Grind it, no complexation because it is already in a boat conformer. There is no sufficient space for the fullerene to get into it, right? So now we have one conformer which is binding the fullerene. We also have another conformer which does not take up fullerene. What would be the next experiment that you can design? You mix these two conformers and then check if the rigid one alone specifically picks the fullerene, right? Then you can say it is a conformation specific binding of fullerenes with the macrocycle. Okay, so that was the thought process. We indeed did that experiment, had both the macrocycles in solution, say 1:1 ratio of these two macrocycles. One is flexible, another one is rigid, and then put 0.5 stoichiometry of the fullerene. Now at any given time the rigid alone should capture this. So that must have resulted a quantitative complexation, right? So 50% of from the solution must have formed a complex and 50% must be remaining in solution, and you can just filter it off, do the characterization, ensure that you have quantitatively recovered that 50% uncomplex, 50% completely complexed, and those are the set of experiment which confirms that a conformation specific binding of the macrocycle is possible. Okay, so this was published in this journal as a cover page, and this was a picture that we made to say that this has a conformational dynamism, right? And if you put fullerene, this also put in fullerene, mix them both and then complex with fullerene, only this captures fullerene and not this. So conformational rigidification, textbook chemistry that we learned, right, from 12th or BSc or MSc, whatever, is now put to application. Initial efforts were by hydrogen bonding or by covalent locking, and now here we show that by simple conformational manipulation you can achieve complex. So this is what we did. Ringa Ringa Coumarins is the title that we gave, right? You form a ring of coumarins and they could do the job of what you were expecting. That's cited as one of the important papers. Anyway, thank you for the opportunity. And this is one part of the work that we do, but we also do other graphene chemistry. Okay, so we can discuss that during the project discussion time. Thank you. Any questions?
Sir,
Yes, yeah.
is it possible to have two 5A compounds around one fullerene? Like, one at one
Like a capsule.
and one at the top.
Like a capsule.
Yeah.
The student is working on it. Your idea is good. Okay. So we thought about it. It doesn't seem to be a very easy task. For supervisor, always it is easy, but for the student, it is, it has to be made. So he's working on it. We know we'll be making it someday. When, we don't know. Oops. Thank you. Thank you.
On behalf of all the students here, I would like to thank Professor Venkatakrishnan for delivering an insightful lecture. Learning about macrocycles and their various uses in real life is very interesting problem. And I really like the part where we learned about the fluorescent nature of coumarin.
Yeah. Thank you.
In conclusion, I would like to say that we had a very astounding lecture.
Thank you.